Okay, hello everyone and welcome back to your YouTube channel. And welcome to this amazing video today. Today the video is related to implementing a test network inside the power system analysis software called IPSA. And as you must be aware, I have been creating a series of videos related with the FGL test system. And today we have the opportunity to implementing that test system inside the software IPSA. So this video is especially dedicated to show you the theory how to implement any test system inside the software IPSA in order to perform power flow. In this case, we are using as demonstration the FGL 3-bus test system, but later you can follow again this video and you can use this video to implement any other test system. So this video is divided in basically two videos. The first video that you are watching right now is the video for the explanation, step-by-step demonstration of the implementation of the FGL 3-bus system using IPSA. And in the next video, I will run the practical demonstration inside the software in order that you can follow all the practicality of implementing this inside the software. So the video today is basically the first, and you will see how to follow the steps to follow in order to implement. And another very interesting comment is that we are using this FGL 3-bus test system. We have been working with this model for a few videos. And if you want to know about the data, about some preliminary calculations, you can go to the YouTube channel and there are a few videos over there with so much information related to that. Well, before we start, I would like to say thank you. Thanks to the colleagues of TNA, that is a consultancy company located in Manchester here in the United Kingdom. They are the people behind the software IPSA. And I would like to say thank you because they allow me to know better this software and also sharing this video with all of you where we are learning how to use the software and how we use the software to perform power system analysis. And this is a video, this is one of the videos in a series because later we are planning to do more complex things with this software. Well, and as you must be aware, this video is just my personal opinions. So those videos are just trying to help people in order to learn more about a specific software, in this case IPSA. But those videos will never be the substitution of the real documentation coming from the software or the real trainings coming from the company. So what I want to tell you is that basically this document is basically complementary or support to the original data and support that is provided by the colleague from TNA. These slides can be found in my ResearchGate repository. Over here you can see the link, and if you want to have a copy of those slides, please go to ResearchGate. That is a very interesting place, social media for academics and scientists, and you can find a lot of useful information over there. As I said before, we are implementing several test networks, and if you want to download them, you can go to the GitHub repository. There is a section dedicated for this very specific video, and you can follow that on the description of this video. Also, if you are watching this video, is because you are in YouTube. And I highly suggest that if you want to keep updated about what we are doing, please subscribe to the YouTube channel. And also, if you have any comment, if you have any critics, if you have any question, please feel free to leave the comment. Also, if you are interested in what we are doing and the most updated information about electrical power system and energy system, please follow us in the social media, specifically on Twitter and LinkedIn. Finally, some of the people in YouTube, the subscribers, they asked me about a personal email that you can contact me for questions, comments, or improvement that they want to see at the YouTube channel. So please feel free to drop an email. The email address is located here at the very bottom, okay? Well, it's time to start. As I say, this is a series of 2 videos, and today what I will do is to present basically the theory. I mean, it's an offline presentation that you can see the steps that you need to do in order to implement the system. For demonstrations, we are talking about the most simple of the FGL test system. In this case, the 3-box test system, okay? We are implementing that inside the software, Power System Analysis Software, IPSA. Well, let me show you the agenda. What we want to do today is we will start with some motivation history behind the test systems, and then I will show you step by step the implementation and the logic behind implementing a test system inside IPSA. In other words, what I will show you today is how we can move from here, that is the single line diagram, into here, that is the basic implementation of the test system inside the software IPSA. So without further delay, let me start with a short motivation. I must be honest, the idea behind the test system, the FGL test system, started in 2007. However, the original idea probably started a few years before. For 5 to 7 years, I was a software developer for creating a new power system analysis software. What I'm trying to tell you is that during my PhD, I started to create this beautiful software for my personal use or for transient stability. And one of the very interesting steps was the module dedicated for the steady state analysis. In other words, the classical power flow. One of the challenges that I faced at that time was having one simple way to test individual characteristics from the network or individual requirements for the power flow analysis. So at that time, I decided to create very small networks, very simple networks that they allow me to test specific details, specific features inside the power flow calculation. And as you can see here, there is a few of them. You can see that time to time the topology is very simple, a single voltage level, but in this case what we want to do, for instance, is to include the capacitive susceptance of the transmission lines. In other networks, a step forward, I start to include reactive power limits. At that moment was basically to show you how to solve the problem of including discontinuities or limits inside the power flow calculation. Also, fit step changers in order to demonstrate the model of the pi model for the 2-winding power transformer with tap changer, and also some other topologies, mesh and radials, and also reactive power compensation. In summary, those test networks, each one of them has a very unique feature that allow you to demonstrate one of the possible aspect to analyze or to model inside the power flow analysis. So initially, I solved all those networks using handwriting, using manual calculations. And then when I finished my software, I compared the numerical results with my software, and that was the simple way that I learned how to include all the effects and features, but at the same time, that was the way that I have a specific numerical step-by-step solution that allow me to test my software and also to debug the software. In 2007, I prepared this document, April 2007, and that was the first moment that those models were released to the public. I remember because in 2007, my bachelor students, they used those models for the classes. Later, I believe 2020 to 21, some of my students in Norway also, they use those models in order to learn to perform power flow calculations. And I don't remember the year, but also in the UK and some other countries in South America, they use those test systems for analysis. Well, later in my life, I start to create those models, those test systems in different computational software, commercial and non-commercial software. And as you can see over here, those models has been implemented using the excellent Power Factory and the very famous and user-friendly software Powerwall. And right now, I will show you how to do this using the software IPSA. And as I say again, those models will be available in the coming future inside the repository, the GitHub repository. Also, at the moment that I am recording this video, in collaboration with some of my colleagues, we are trying to publish a paper where we also implemented those models using digital real-time simulation. So the idea is offer to people the way that they can learn different features and different characteristics of the load flow, and at the same time they have the possibility of obtaining the detailed numerical solution. But well, let me start this video officially, because today what we want to do is implementing the FGL 3-bus test system inside the software IPSA. And I will start describing this very simple, very straightforward test system. This is what we call the FGL 3-bus test system. As the name says, there are 3 buses over here. There is a single voltage level. There are no transformers here. I know that many people believe that this is unrealistic. Of course, every single generator requires that up transformer before going to the transmission system, but connecting directly the generator to the bus bar, the transmission system, allow me to simplify some of the calculation for the students for manual calculation and obtaining very simple results. Well, as you can see, this is a single voltage level system, and there are 3 transmission lines over here, one between bus bar 1 and 2, another 2, 3, and one more between 1 and 3. There is a load over here, 400 megawatts and 200 MVR. For that reason, this is a bus bar that we define as PQ bus bar inside any power system analysis. And in this PQ bus bar, of course, we have 2 unknown variables, the magnitude of the voltage and the angle. On bus bar number 3, there is a synchronous generator here. This is the generator 2, and the generator 1 is connected to the bus bar number 1. This generator 2 is operating to keep constant the voltage at bus bar number 3, and in this case, the numerical value is 1.040 per unit. And this generator is also providing constant active power. In this case, the dispatch is 200 megawatts. So as a consequence, this bus bar inside any software is referred as PB bus bar. And the unknown variables for this case are the angle of the voltage and also the reactive power. And in this model, we have a very interesting feature that we want to show regarding controls in the power flow. In this case, in this model, we are considering that the reactive power generation of this machine over here, this synchronous machine, the reactive power must be between minus 20 MVR to 40 MVR. So this is what we know, limits for reactive power. And finally, we have the bus bar number 1, we have the generator 1 over here. As you can see, the full details of the voltage are known. In this case, the bus voltage is 1.05 and the phase angle of that voltage is 0. So this is a classical slack bus bar because we know the voltage magnitude and angle, and the unknown variables in this case are the active power and the reactive power injection. So this is basically the explanation of the network. And over here, you can see that this test system, we can identify, we can find the data. We have the bus data, we have the branch data, and the generator data. In the bus data, it's very easy to recognize that there is a single voltage level from 115 kV. Here is the data for the active and reactive power of the load number 2 here. And also we can recognize that we have the series resistance in ohms per kilometer. We have here the series inductive reactance in ohms per kilometer. And finally, we have here some very interesting detail for the generators. Generator 2 is type 2. That means is the slack bus bar. Generator 3 connected to the bus bar number 3, is a PV, and that means that there is some limits over here, minus 20 and plus 40 MVR. You can find this data, you can go to the ResearchGate repository, the link is below here, the video, and also you can download the detailed data of this test system, okay? Well, let's move forward. As you must be aware, the software IPSA, the power system analysis software IPSA, requires the data, the input data, for instance, for the transmission lines using the per unit system. So the first step is having all the data or converting or referring all the data into the per unit system. The good news is that we have been recording several videos, and we also create some MATLAB live script for the calculations of these per unit values, okay? If you want to see the MATLAB live script, what you need to do is go into the GitHub repository. The link is over here, and you will find the MATLAB live script, and you will be it will be extremely easy to calculate the per unit values. And also here there is a video where we have the full explanation about this MATLAB live script and how to obtain the per unit values for this test system. And without further delay, let's start the implementation of the FGL 3-bus test system using the software IPSA. What I want to tell you before I start the explanation is that this video is created by me, and also this sequence that I will show you here is again created by me. The colleagues from IPSA, they have trainings, they have classes, they have documentation, and here what I am presenting is just only my vision. It's only my idea, the basic steps that I call here parts that you need to follow in order to create a simple test system inside the software and perform load flow, as they call it, or power flow. Okay? Well, for me, they are a part 1 that we are creating the graphical representation or the network model inside the software. Basically, what you are doing is using the graphical objects inside the software in order to create the single line diagram. But this single line diagram is empty of the most important data, So the part number 2 is introducing the network, the data, the parameters inside the network model. When you finish including all those network data, we need to go for the part number 3, and that is basically preparing the software and the model in order to perform the load flow. And there are two very important parts over here. The 3.1, that is basically defining the slack bus bar, and then we can run the power flow. And when we finish running the load flow, one of the interesting features about IPSA is that you can get their numerical results of the load flow or power flow inside the graphical representation. So the final step is configuring the display of styles and results inside the software. That is basically 4 parts. And if you follow in this very systematic way those parts, you will be able to reuse this video and you can create any other test system. And remember, this test system will be used for power flow, or as my colleague of IPSA call, load flow. And I am making this very specific remark because if you are planning to run short circuits or transient stability, that is another history, and we will be covering that in other videos, okay? Well, without any delay, let me start creating the network model. Creating the network model is very simple because the software is quite user-friendly, so it will be extremely simple. Let's start with the step number 1, and what we need to do is go into the desktop, or in your program list, you identify the icon for IPSA, double-click over there, and you are executing the software. When you execute the software, there is a welcome window. And as you can see over here, this is the welcome window for the IPSA version that we have inside the DIgEnSysLab. And in this case, you can see that this is an educational version. That means that this software is only for students, for research, and is not for commercial use. And again, those videos, there is not commercial relationship with anyone. The YouTube channel is totally independent. We need money. But this YouTube channel is only for your use, okay? So the step number 2 is we will say okay in this window, and the step number 2 is creating the network. To create the network, IPSA is identical to any other software. You can use shortcuts using your keyboard, or you can use what I call the formal way to do things. That is basically following very basic step using the classical menus. So if you are a classic person like myself, what you need to do is going here to the very top, and you can see here File, and then when this window opens, you will say New, and then New Network. In that case, you need to do 3 very basic steps. Step number 1, step 2, step 3 over here, File, New Network, okay? I prefer this approach because people can be engaged with the different windows, and in those windows you can see more features and more modules and more information that can be useful later. However, if you are a top expert level, probably you would like to do the thing in the faster way. And the faster way to do this is basically using the keyboard shortcut. And the keyboard shortcut is very simple. Control-N is identical to any other software like Microsoft Windows. Control-N is a new document. Inside IPSA, Control-N, N for November, is basically creating a new network model, okay? When you do that, Control-N, you will see that in front of you, you will find this window. And this is the step number 3, because you need to provide information about the network. And in this case, we are creating here a new network, and we define this network using a single line diagram. So it's a very simple step. Just select here single line diagram. From there, you go to nets, okay? And when you press nets, automatically IPSA will present this window over here. That is our step number 4. The step number 4 is that you need to tell the software about the properties of this single line diagram or the graphical object as the diagram properties, okay? In this case, we will define a name, and because we are working with the FGL 3-bus system, well, there is nothing different here. We will use FGL 3-bus test system. I am using here this very interesting symbol. This is the underscore, and I use underscore because there are some operating systems that they are very, very scary to use the space. So I prefer to use underscore every time that I am naming something new, okay? Perfect. When you complete the name in the diagram properties, just press the button Next, and we will go to the step number 5. Step number 5 is very important step because in this step we are defining the network properties. And here is where you need to define the base. Because if you remember a few minutes ago, I told you that IPSA is a software that is working using per unit quantities. So every time that you are working with per unit quantities, you need to define a apparent power base. And in this case, we are using the data 100 MVA, but also you need to define the rate frequency or nominal frequency. And in this very specific case today, we are using 50 Hertz. Also, you can include a title for this network, and also you can define here a author, okay? There is a typo here in my surname. Well, we will solve that problem later, okay? But again, this is a very, very simple step. This is the step number 5. When you press over there, finish, well, we are going into the step number 6. Because the step number 6 is that IPSA create a canvas, an empty page, and is a graphical page over here. You can see here in the center area. You can see that is totally empty, and that is the place where we locate all the components of our single line diagram. So we are ready to start to build, to create our electrical power system model inside the software. And that is the step number 7. The step number 7 and the remaining steps are related with creating the graphical object that is basically the single line diagram. Well, now we are moving into the step number 7. And the step number 7 is basically including the different components of the power system. We will start with the bus bars, and IPSA is a very graphic and user-friendly software, so we can use the classical drag and drop technique. On the right-hand side, you can identify there is a toolbar that you can find all the graphical icons representing different components of electrical power system. On the right hand, at the very top, you can identify a straight line, and that straight line is the symbol for a graphical object representing the bus bar. In this test system that we are implementing, we need 3 bus bar. So what we will do is select here and drop over here bus bar number 1, bus bar number 2, and bus bar number 3. As you can see, I try to locate those bus bar in a place that allow me to follow the graphical representation of the single line diagram. Well, after the step number 7 of inserting the bus bar, step number 8 is dedicating to the loads. However, in this system, we have only a single load that is connected to the bus bar number 2. So again, we are using the drag and drop. We are selecting the object for this beautiful load and connecting the load at bus bar number 2. And it's done very simple and very easy. Then step number 9 is dedicated for inserting the synchronous generators. In this FGL 3 bus bar system, we have one generator connected at bus bar number 1 and another generator connected to bus bar number 3. And to do that, what we need to do is basically select here the icon, clicking on the bus bar, and we are dropping over there our 2 synchronous generators. Finally, the remaining component is the branch component. In this case, is the transmission line. And you must remember, we have 3 transmission lines over here, one between bus bar number 1 and 2, another between bus bar 1 and 3, and finally one more between bus bar 2 and 3. And to insert those transmission lines, we can do it is basically clicking on the front bus and clicking on the end bus. If you want to learn more about how to do this, you can go to the user manual of IPSA, okay? And you can see that the icon for those transmission lines are located over there. Well, here we installed the 3 different transmission lines, and congratulations, because now you can see the full system topology implemented inside the software IPSA, and well done, you create your first ever single line diagram inside the software. However, the bad news over here is that this is a graphical representation of the power system. The components are located over there. The information of the parameter are missing. So what we need to do in the part number 2, what we need to do is basically introducing the data parameters related to the network model. And to be honest, step number 10 is we will start to change the data or input the data inside every single component. IPSA is a graphic, very user-friendly software with graphical interface, and you can go into the single line diagram and double-click on the component. In this case, we will go to the bus bar number 1, and we are double-clicking on the bus bar number 1, and you can see that this window for bus properties is open. And what we will do over here is changing the name. We will call this bus bar just bus bar 1, and we are defining here the rate voltage, okay? In this case, this is a 3-phase system, so the rate voltage, as usual, is a line-to-line voltage RMS. And in this case, because the FGL3 bus bar test system, the data say that the voltage, nominal voltage, is 115 kV. So what you need to do is changing those data over there and then press OK. Then we will do the same for the bus bar number 2. Bus bar number 2, we are using the name, just the number 2, and the rate voltage is 115 kV. We will do the same for the bus bar number 3. Double click on the bus bar number 3, change the name. The name will be the number 3 alone, and then we are including over here 115 kV as the name, okay? Press OK, and we complete the data, the parameters required for this beautiful bus bar. Now what I will do is introduce the load properties, and it's again very simple. We double click in the load, on the top of the load properties are open, and we are defining the name, load number 2. We are defining the active power, in this case 400 megawatts, and we are defining the reactive power. In this case, the reactive power is 200 MVR, okay? 200 MVR. You can see that also IPSA is showing the values for the apparent power and the power factor, and those values are calculated basically using this active and reactive power input. Next step is we need to go to the transmission lines. We have 3 transmission lines. Let me start with the first one, the line 1, 2. We are using as a name line 1, 2, and we are introducing here the values for the series impedance of this transmission line, in this case the resistance and the reactance. The resistance in per unit quantities is 0.02, and the reactance, inductive reactance, series inductive reactance is basically 0.04. And finally, we are defining the length, and the length is 1 kilometer. We will do the same for the transmission line 1-3. Transmission line 1-3, we change the name. We introduce the resistance 0.01 per unit, and the series reactance, inductive reactance, 0.03. And the total length, again, 1 kilometer. Finally, we have one more transmission line in order to complete the data of the transmission system, and that is the transmission line 2-3. To complete the data, very simple, double click on the transmission line, change the name, this is the line 2-3, then define the total series resistance in per unit, 0.0125, and finally define the series inductive reactance, 0.025 per unit, and the total length. Remember, when you complete the data, press OK, and everything is stored, the data is stored inside the database of the software, okay? Perfect. We need to define 2 more parameters related to the generators. And generators, again, is extremely simple to configure. What you need to do is double click, and the generator properties open, this beautiful window that you can see over here. And what we need to do is define the name, in this case G3, and in this case, remember, this is a PQ bus bar. And in this PQ bus bar, we need to define the magnitude of the voltage. In this case, the setting is 1.04 per unit. Then we need to define the active power, in this case the dispatch, and the dispatch is 200 megawatts. Finally, remember, we have limits for the reactive power production of this generator. It must be below or equal to 40 MVR, and it must be from minus 20 MVR. So here in this section is very important that you configure the limits for the maximum and minimum reactive power generation, okay? You can do something similar. You can do something similar for the case of the generator number 1. Well, we have complete all the data. We have complete all the data for the network model. However, we are interested on producing results, numerical results of power flow. So in the power flow, a very interesting feature that I found in IPSA, probably is a unique feature that you will not find in many other software that I can remember, Probably I'm wrong, sorry. But inside IPSA, you need to define the slack buses, and there is a dedicated section to define the slack buses, okay? You must remember that the slack buses in the power flow are defined by magnitude and angle. In classes, in classical power system analysis, we typically use a single slack bus bar. However, in real power system, we can have one or more slack bus bar. So IPSA is defining the slack bus bar using a very peculiar, very unique way. What you need to do is, first, you need to go here at the top to network, and then scroll down and you will go to slack, okay? Because this is the way that IPSA obtain the information of which bus bar is defined as reference swing or a slack bus bar. Go to network, then to slacks, and when you do that, this menu will open in front of you. And in this menu, what you need to do is select the swing or slack bus bar from all the available bus bars. So as you can see here on the left-hand side, in this test system, we have 3 different buses, 1, 2, and 3. But for the FGL 3-bus test system, the bus bar number 1 is the slack bus bar. So we need to highlight here and then press this button in order to select. And finally, you will see appear the bus bar over here, number 1, as the selected reference or selected slack bus bar. So then you will press OK. When you do so, what you are doing is again selecting or defining the location of the slack bus bar. Again, probably my friends in IPSA, they will be laughing about me because I found this quite peculiar, okay? Each software has different ways to the selection of the bus bar or the definition of the slack bus bar. I found this quite interesting. Probably I need to have a conversation with the colleagues over there to understand better the motivation of this way to select the slack bus bar. But well, now you know how to do it, and we are ready for running the power flow. Well, here we have the step number 4, the part number 4, and that is basically we are running the power flow. And IPSA is similar to many other power system analysis software. IPSA has this toolbar here at the very top. And what is interesting of this toolbar over here is there is a location for an icon, and you can see that the icon is like a bus bar with some power input and some power output. This icon over there is dedicated for the power flow calculations. Well, the colleagues from IPSA, they call load flow, okay? When you press this icon over here, this button over here, you open the load flow properties. And in this window, what you are able to do is basically defining the features, characteristic of the load flow calculation that you are performing. For instance, you can change the tolerance for the error in your load flow calculations. Or you can change over here the maximum number of iterations that you are allowed to run for obtaining the solution of the load flow. For this video right now, I will not change any of these parameters. I will keep the configuration of the load flow properties as it, and I will just press the button over here. And when we do that, well, we are ready to get the results. And remember that IPSA has a very powerful graphic interface where you can retrieve the results, numerical results of your power flow, looking into the single line diagram. And to be honest, the part number 4 of these steps that I am presenting over here is configuring the display and styles and results. So what I will do now is very simple. If I want to configure the results display styles, it's very simple. You put your cursor anywhere here in the graphic area, empty graphic area, and you click the right button of your mouse. When you right-click the button of your mouse, there is a context menu, and you can see over here, this is the context menu that you will find, okay? This is a property similar to the context menu that you can find in Microsoft Windows, in Windows and any other applications like Microsoft Office, etc. Okay? And the third option over here is result display styles. And if you press over there, a window will appear. And in that window, you can see over here, you can configure the styles and results for the bus bars, radials, and also branches. For the bus bars is quite interesting because you can present results in per unit quantities. You can present results using real units, I mean kilovolts in this case. And also you can use here some definition for colors defining voltage limits, okay? Also, you can do the same for the radial components. In the radial components, you can create an arrow to define the direction, and this direction can be configurable, customized for real power, reactive power. You can use animations, and again, you can use colors, okay? In this case, we can use to represent the real power, for instance, or the active power, and also for the branches, we can do the same. For the branches, we can configure presenting the real or the active and reactive power. We can configure the units. And in this case, I am defining that the graphic will be animated because I would like to show my students how the power is generated, in this case, the active power, and the active power is moving inside the transmission system and going to the load. And when we do that configuration, well, we are ready. And look over here. This is the final step. In this final step over here, you can recognize that I am presenting the results of the power flow. What is interesting for me, and probably quite interesting for the students, there is no arrows. You can see over there are some dots that they are moving on the components, okay? But what is really interesting is that the size of the dot is proportional to the power that is moving on the components. So as you can see over there, for instance, the transmission line 1 to 3, the active power is only 35 megawatts, but on the transmission line 1 to, the active power is 182 megawatts. So you can see the size of the dot on the transmission line 1-2 are bigger than the transmission line 1-3. But if you go into the transmission line 2-3, the active power is even larger, is 226 megawatts. So the dot, or the small red point that is moving on the transmission line, is even bigger. But when those two power flow arrive to the bus bar number 2, you must remember we apply the power balance equation. all the active power arriving to the bus bar number 2 must be equal to the power that is leaving the bus bar number 2. So you can see that they are arriving over there, 2 dots, and then the dot that is leaving on the load number 2 is representing the 400 megawatts of that load. And you can see that that dot, red dot, is even larger. So it's quite interesting, okay? And also is very important, you can notice over here that we are obtaining the voltage at the bus bar number 3, and also we are obtaining the angle minus 2.7 degrees at the bus bar number 2. And for the bus bar number 3, you must remember that in this case, the reactive power production, it was an unknown variable, but in this case is 40 MVR. And that is the maximum reactive power that can be produced by this generator. And also we obtain over here the phase angle of this, that is minus 0.1 degree, and we obtain P1 and Q1, active and reactive power of the generator number 1 at the slack bus bar, okay? Well, I am sorry that I'm not making so many comments about numerical results here. I can do a further analysis. But again, this video was just to tell you the basic steps that you need to follow in order to create the model of this FGL 3-bus bar test system inside the software IPSA. It's not to analyze the load flow result, power flow results, okay? Well, we are reaching the very end of this video. Right now we are reaching the end, and I must tell you that in this video we present the theory, the basic step that you need to follow in order to create the single line diagram, to complete the parameters of the data of the system data that you need in your model, then defining the slack bus bar, and finally running the load flow. And I did this video in order that you can understand those steps, and then you can extrapolate, or you can use those steps in any other model. I must be clear, those steps that I am presenting over here, they are my personal opinion. I create those steps in order that you can follow and create the network, but this is only for power flow analysis. If you want to run short circuits or transient stability or any other study inside IPSA, well, keep in touch because you need to watch more videos. Finally, before I go here, I would like to tell you that this is the end of the first part of this series, and in the next video I will go inside the software and I will create this network step by step, and you can see how to do this beyond just basic screenshot. Well, this is all for this video. Thank you very much for watching, and it's bye now.